Good evening, everyone. Today we will be presenting our research on finding the volumes of hyperspheres using a technique of multiple integrations over multiple dimensions. Now, what exactly are dimensions? Well, we can simply define a dimension by saying that it is the number of coordinates needed to place a particular point in space. Now, some common examples of dimensions are the one-dimensional coordinate system, in which you usually have just a straight line in one direction. The the two-dimensional coordinate system. It's the more traditional system. It involves the x and y axes, and the three-dimensional coordinate system. Now, in this, we have the z-axis in addition to the x and y axis. Moving on to our questions, our first task in determining the formulas for hyperspheres was to determine the area of a circle using using double integration in the two-dimensional coordinate system. Let me just switch to my working. This is a circle in the two-dimensional coordinate system, the x and the y axis. Now, we know that the equation of a circle in the Cartesian plane is r squared is equal to x squared plus y squared. Now, from here, we can determine that y is equal to the square root of r squared minus x squared. And also remember that in the polar coordinates, x equals r cos theta and y is equal to r sine theta. Now, moving on over here, we're required to use double integration and trigonometric substitution together with this formula as well. So now, first, how to solve a double integral. Now that's pretty straightforward actually. Like over here, I have set up a double integral with a function inside. Now in this case, the function is 1, and we need to integrate it first with respect to x and then with respect to y. Now, when we're integrating it with respect to x, we only look at these two limits. Now, as the internal function was 1, it simply becomes x, and then we insert these limits, and then we integrate it with respect to y. Now, in order to find the area of the whole circle, what we are doing right now is we're finding the area of this quarter portion. So that's going to be the radius, and the angle is going to be pi upon 2. So that's why over here we have a 4, and these limits are simply the limits for x and for y after we integrate. Now, when we reach this stage, now to make the integration a little bit easier, we can use trigonometric substitution. Over here, we substituted y for r sine theta, and that becomes, when we resolve this whole thing like this, it eventually resolves down to r cos theta. And then since we already had an r cos theta over here, was in order to change dy to d theta, we need to find it from here, and dy is equals to the differentiation of sine is cos, so r cos theta d theta. So that's why we replace the whole thing over here. Moving on, we eventually reach down to r square cos square theta. Now over here, since r square is going to be more as a constant, we can take that outside of the integral and just integrate for cos square theta. Now cos square theta by the table of integrals over here, the integral of cos square u is equals to half u plus 1 upon 4 sine 2u. So when we apply the limits 0 and pi over 2, we end up with pi over 4. And after that, we still have to multiply it by 4 because this is the area for the quarter circle. And then when we multiply it by 4, we end up with pi r square, which, as we know it, is the area of a circle. Now, my teammate Aisha.
Discussed with us how double integrals are computed. But what I want to share with you guys is what gives us this particular magnitude of number. What gives us the double integral? And so if you see, we have this object that we need to find the volume for. And if we if we cut this object into slices like a pizza, uh, we see that a very small slice would have a section of a height of z, which is the which is along with the z dimension, right? And if we cut this particular slice, this one slice, into further rectangular sections, we have this height. And then if we find individual rectangular areas and multiply it with the height of each of the rectangles and sum them up, we have a volume of total volume of that particular slice only. But if we sum all of these similar sections or slices, we have the volume of the entire object. So the idea is that we're double integrating because we have the first integral is for the summing of the sections that we cut of the slice, of that one particular slice, into rectangular sections. And then we sum all of these similar slices into one particular object, and we have this one volume. And so what Ahmed did was, we were basically multiplying the height of that z that we just saw was equal to 1 and was giving us the area of the circle. Now Aisha would be introducing us to the concept of triple integrals.
Now we will discuss the triple integral and how it will help us get to the volume of a sphere. We further integrate the result of the double integral, which usually gives us the area or under or inside a region, to move into an additional dimension and calculate the volume of a shape. As we are dealing with spheres in our presentation, it is safe to assume that it is the equation of a circle which will help us reach the volume of a sphere, since the rotation of a single circle in a 3D plane results in the formation of a perfect sphere. The equation of a circle in 2D is x squared plus y squared equals to r squared, and if we alter it for 3D, it will become x squared plus y squared plus z squared equals to r squared, where z is the additional axis. The pictures show the change of a circle to a sphere from 2D to 3D. This was a very basic background of what we are going to discuss. In the Cartesian coordinate system, the location of a point in space is described using an ordered triple in which each coordinate represents a distance. In the cylindrical coordinate system, the location of a point in space is described using two distances, r and z, and an angle measure theta. In the spherical coordinate system, we again use an ordered triple to describe the location of a point in space. In this case, the triple describes one distance and two angles. Spherical coordinates make it simple to describe a sphere, just as cylindrical coordinates make it easy to describe a cylinder. Grid lines for spherical coordinates are based on angle measures like those for polar coordinates. By convention, the origin is represented as 0, 0, 0 in spherical coordinates. You can see the detailed description of the spherical order triple in the slide. They are the Greek letters rho, theta, and phi. The diagram clearly illustrates the positions of these angles and the distance rho in a three-dimensional plane. This system is very handy for calculations when we are dealing with spheres of different radii. However, one very important way to calculate the volume of a sphere is through triple integration, which also involves trigonometric substitution. In the middle of the slide, you can see the equation of a sphere we discussed earlier. We can now substitute the equation to make z the subject. This will give us a little idea about how we are going to find the limits of the integrals. We know that we will be integrating dz, dy, and dx, so it makes sense that the limits will be in terms of x, y, and z. Since z is the first to get integrated, as you can see in the equation below, the innermost limits will be in terms of z. That is, the positive and the negative value of the formula we found out earlier. You can look above under the heading of the limits to see it clearly. After z has been dealt with, we will do the same thing to x square plus y square equals to r square by making y the subject now. It will be done one more time where now x is the subject. After writing the limits, the equation will look like how it is shown below. In order to find dy over d theta, we will keep in mind the fact that theta is positive pi over 2 for the positive y equation and vice versa. Therefore, we can write y equals to under root r square minus x square multiplied by sine theta, which will turn into r square under root r square minus x square multiplied by cos theta after we integrated for theta. Now we can follow the general rules of integration using trigonometric equations like cos square theta equals to 1 minus sine square theta to find that in the end we will result in the volume of a sphere, which is 4 over 3 pi r cubed.
So, the world which surrounds us is often viewed as only having three spatial dimensions. However, just as we can represent some structures in lower dimensions, there can be higher dimensions too. In geometry, we may compute the volume of an object which is reliant on only three factors: height, width, and depth. Yet what happens if you want to model something which is reliant on 4, 5, or even thousands of factors? This is where higher dimensional functions are used. Since the space we live in is three-dimensional, but once we move on to higher dimensions, you'll see the intuition is mostly gone, leaving us to rely on mathematical analysis. So as for a sphere, it's easy to define a sphere in any dimension. It's all the points that are at a fixed distance away from a central point. On the two-dimensional plane, you can imagine holding a rod fixed at one end and spinning at the other end to trace out a circle. In three dimensions, the same trick works, but now the rod has more freedom to move and traces out a sphere. In higher dimensions, this traces out a hypersphere. A 4D sphere is to a 3D sphere as a 3D sphere is to a circle. Since there are four mutually perpendicular axes at play in a four-dimensional space, a sphere in four dimensions is just a 3D sphere that doesn't utilize the extra dimension. You may look at it this way: if you pushed a three-dimensional ball to a two-dimensional surface, like a table, the portion of the ball intersecting the surface would always look like a disc first, a tiny disk, getting bigger and then getting smaller again. The disk is a 2D slice of the ball. If we took a 4-dimensional ball and pushed it through our 3-dimensional world, we'd see it as a 3-dimensional ball. First a tiny ball, then bigger, and then smaller. These are the 3D slices of a 4-dimensional ball. After 4 dimensions, our visual imaginations are pretty much useless. But we can also assert that if you take a disk from a four-dimensional sphere, that disk is essentially a three-dimensional sphere. Now, if you sum the volume of all these disks in that four-dimensional sphere, we get the volume of the four-dimensional sphere, which is essentially the mass of the sphere. Now look at the axis which represents the first variable and the y-axis which represents all the other variables. Suppose that you just took the slice of this ball. So again, maybe you think of four dimensions. If you slice the ball in four dimensions, you actually get at this, which is a ball in three dimensions. So a four-dimensional sphere points a sphere with four coordinates. A 4D sphere can be thought of as a set of points such that x squared plus y squared plus z squared plus w squared equals to r squared. Here w is an additional coordinate. The easiest way to imagine a 4D sphere is as space to time, where the 3D sphere's radius r equals to square root of r square minus w square. We can use the symmetry of this equation to say that it is equivalent to say that x square plus y square plus z square is equal to r square minus w square, such that we are adding a three-dimensional sphere with a varying radius of square root of r square minus w square over w, as w goes from minus r to r. So the volume of the three-dimensional sphere with radius of square root of r square minus w square will essentially give us the volume of the sphere in four dimensions. Now, as the name suggests, a quadruple integral is just integrating four times, and at each integral level, our limits have one less dimension, as I talked about it in the last slides. We also may compute the volume of a 3D sphere, which essentially has the radius of square root of r square minus w square, and which will give us the volume of the 4D sphere. Then by integrating it from minus r to r, we get this, and then by using the trigonometric substitution of w is equal to r sine theta, we get 8 pi r to the power 4 over 3, and we have to integrate cos to the power 4 theta from 0 to pi by 2. I may have skipped some working since I am short on time, but you guys get the idea, right? So as we integrate this, we get our formula for the volume in four dimensions, which is essentially pi r to the power 4 over 2.
Now, having been established what triple, quadruple, and double integrals exactly give us, the question arises, what exactly do we do about the higher dimensional hyperspheres? The 20th dimensional hypersphere, the 30th dimensional hypersphere. So what we have here for you is a pattern that we realized in process of integrating individual integrals, and the nth integral we realized is this particular equation. But the equation itself is very complicated, and we can't use it, and is not really helpful in terms of efficiency, right? And so these integrals that we have in front of you is the second integral till the seventh integral, and visibly, quite visibly, we have this pattern that separates the double and the even and odd integrals. We have these constants that we have in front of the integrals themselves, and if you look closely, we see that they are essentially the volume divided by the radius. The volume itself, the magnitude of the volume of the one less dimensional hypersphere. So for example, the third integral has an integral of itself and then a pi associated with it, right? And we know that pi is the volume of a sphere which has a height of 1, right? And this volume we extract, or we have it from the second integral, which is one less dimension integral. And so yeah, we see that, okay, so this there's this pattern. So how do we conclude that particular pattern? This is what concludes it. We see that the volume of the one less dimensional hypersphere divided by the radius, the radius and the power to the one less dimensional hypersphere multiplied by the integral itself, we have this volume of that particular dimension. For odd and even integer integrals, we have different equations, and where k is equals to n minus 1 and x equals to r sine theta. We realize that x is there also, and so we can substitute r sine theta into it, and we can find this alternative equation which constitutes cosine theta. So this brings us to the end of the